Hello, physics students. In this tutorial, we are going to cover the idea of free fall. How do we know when an object is in free fall? What does that mean? Well, I'm going to give you two examples of objects that are in free fall that are very familiar to us. Okay, so the first one, we have an object here. Let's give this person some hair and a face. Okay, so this object throws a ball up into the air. Right as it leaves the hand, it has an initial velocity, but then it starts to do what? Well, we know that it's going to slow down, and then it's going to stop just for a moment and turn around and speed back up, coming down until it gets to the hand. So we're familiar with this type of motion. We've all probably thrown a ball up into the air, and we know that it's going to follow this path, and there's a specific reason that it follows this path. There's something that slows this object down as it goes up and then speeds it up as it goes down. Okay, let's look at the next example. We have an object that is being released. So here's another guy. Here's his face. And he has a ball and he's dropping it down. And he releases this object from rest. And then right as he drops it, it's going to speed up until it hits the water below. Again, we've probably accidentally dropped things, and we see that they speed up as we drop them. So what do these two have in common? Well, both of these objects, believe it or not, are in free fall. Sometimes people get mixed up because there's the word fall in it, and that doesn't always mean that it's moving down. A free-falling object is anything that is anything that's under the influence of only gravity. That would be an object in free fall. So if we look at both of these, the object on the left is being thrown up, so even though it's not moving down, it's still in free fall because it's only under the influence of gravity this whole time until it gets back to the hand. That is, gravity is going to actually slow it down and then speed it back up. Likewise, this object over here is being released from rest, and immediately it's going to speed up. Now, the cool thing is that any object, no matter how big or small it is going to fall at the same rate. So if we were to measure how fast this object is moving at every second, we would see that there is an increase in velocity. From 0 here, every second it would increase in velocity by 9.8 meters per second. Every second. So we call this vertical acceleration due to gravity, meaning that gravity is the reason that the object is speeding up or slowing down. On the right here, it would be speeding up. On the left, gravity would actually be slowing this object down and then speeding it up. But either way we look at it, there is a constant acceleration here of negative 9.8 meters per second squared. The magnitude is 9.8 meters per second, and the direction is downward. That's why it would be a negative acceleration. And just a quick reminder, acceleration is just simply a change in velocity over change in time. So while the object on the right here is speeding up, which is a change in velocity, the object on the left is slowing down and then speeding up. All of that is experiencing the same acceleration. So the same rate that the velocity is being changed by. So we are going to focus on this idea that we have a vertical acceleration due to gravity, and it's a constant acceleration of negative 9.8 meters per second squared, or 9.8 downward, which is negative. So we're going to come to find that free-falling objects are really just kinematics with a vertical twist, if you will. So I like to refer to them as vertical kinematic problems. And again, this is only when we have objects that are only under the influence of gravity. Now, to backtrack a little, when we dealt with horizontal kinematic problems, or objects that had a horizontal acceleration, we were given things like initial velocity, final velocity, change in time, displacement in the horizontal direction, which is why it's change in x, and then acceleration. When we deal with vertical kinematic problems, we deal with the same exact variables, except there's a couple little differences. Initial velocity is still vi, final velocity is vf, change in time is still change in time, except we see something here. We see that change in y is now what we're calling displacement, because before it was a horizontal displacement, or on the x-plane, and now a vertical displacement would be a change in y, because it would be the y-plane. And then we still have acceleration. Now, for free fall problems specifically, meaning, again, the object is only under the influence of gravity, whether it's thrown up into the air or dropped from a specific height, we have two ideas that are different. As I just mentioned, the vertical displacement is now called change in y. And the cool thing is that if something is in free fall, we automatically know that the acceleration is negative 9.8 meters per second squared, because it's a downward acceleration. So pause this if you need to, make sure you're writing this down, and we're going to jump into a problem right now so that we can really see how this works. Okay, so Chuck is riding the giant drop at Great America. If Chuck free falls for 2.6 seconds, what will be his final velocity, and how far will he fall? So it looks like we're looking for two things here. And we're also given a couple things. We know that he's free falling for 2.6 seconds, so that's a measure of what? Time. And because this is a ride, we know that when you get to the top of a ride, you kind of pause for a moment, right? And then you would go into free fall. So we can also assume that the initial velocity is 0 meters per second here. So here is the list of givens on the left here. And we have initial velocity is 0, final velocity we don't know, but we're looking for change in y, or vertical displacement, is going to answer how far he's going to fall. Change in time is 2.6 seconds, and acceleration is negative 9.8 meters per second squared, because this object is in free fall. It tells us right here in the problem. So as I mentioned before, free fall problems are vertical, and they're also kinematic problems because we're dealing with constant acceleration. So we need our list of kinematic equations. So there it is, and let's start by finding the final velocity, because that's the first thing that's asked for. You don't have to solve for that first, but I'm just going to pick that one to go for. So we have to figure out which equation to use. Which equation has the things that we have and the thing that we're looking for? So I have initial velocity, I have change in time, I have acceleration, and I'm looking for final velocity. That means I don't really care about my change in y. And for the equations over here, we could actually change in x to change in y. All right, so which equation does not have change in y in there? Because we don't really need it right now. And if you look carefully, the very first one has everything that we have and everything that we're looking for in the moment, because we're looking for final velocity. Okay, so I'm going to rewrite my equation. That's an important step. Vf equals Vi plus A. Oops. Whoa. Vi plus A times time. Okay. So now I'm just going to start plugging in Vf equals Vi, which is 0, plus negative 9.8 meters per second squared times 2.6 seconds. One of the seconds will cancel out there. So it looks like I'm just left with a little multiplication. So because 0 We can cross that out. So final velocity, if we multiply negative 9.8 times 2.6, we get 25.48 meters per second. Now, we have to be careful because this is going to be a negative final velocity. Why would that make sense? Why is it okay that we got a negative number? Well, we know that Chuck is riding and he's dropping. So we know that he's going to be moving downward, and we're going to consider downward negative. And so that's why it's okay that we got a negative number for our final velocity. Okay, so we're going to cross out this problem because we're not solving that. And I want you guys to pause the video, and I want you to try to find the second part of this question. How far will Chuck fall? So again, we're going to be looking for displacement in the vertical direction, change in y. So I want you to pause the video, try to find the equation, write it out, and then solve the problem. Ready, set, go. All right, here we go. Let's see how you did. Now, the cool part about this is that you could have actually picked any of these equations here. The only one we can't use to find change in y is the first one because it doesn't have it in there, so we wouldn't be able to solve for it. But since we have all of the other variables, we can go ahead and pick any of them. So I'm just going to show you two different ways. So maybe you chose the last equation. So we're going to bring that over here and we're going to rewrite it. Change in y equals 1/2 times vi plus vf times time. Okay, so I have 1/2 times 0 plus a negative 25.48 times 2.6. Now, these two guys are going to make a negative, right? So we really have 1/2 times negative 25.48 times 2.6. So if we do that math, we get a vertical displacement of 33.12 meters, and it is negative. Why does it make sense that we get a negative number? Because he's falling down. So the vertical displacement, where he starts to where he finishes, is negative. Okay, so what if you used let's say the first one up here, or the second one, but it's the first one that we can choose. All right, so let's try it again because we should get the same answer. All right, so change in y is 0 times 2.6 plus, there we go, negative 9.8 times 2.6 squared. Now, you have to be careful here because we have to square the 2.6 only, not anything else. And then we can do the rest of the math. And we know that the initial velocity is 0, so this is going to cancel. So we are left with 1/2 times negative 9.8. I'm going to go ahead and square that, which comes out to 6.76. Okay. So, last little bit of math here. And we get the same exact answer, which is awesome. So, that is a free fall problem for you. Hopefully you got it right, and please write down any questions you have, and we'll do lots and lots and lots of practice in class. Thanks a lot for watching. Bye.